So let's take all of this information about work and potential energy and kinetic energy and put it together. We'll do this using a roller coaster example. All right, in order to do this, let's go ahead and take a look at two terms. First, conserved energy, and then closed system. In order for us to understand conserved energy, we need to realize that matter, and in this particular case, energy, is neither created or destroyed. It is simply changed from one form to another. Now, this can only really be observed if we have a closed system. A closed system exists when all forms, in this case of energy, are basically measured and counted. Let me give you an example. Let's say I have a room, and in this room I put two guys. One of them I'm going to call potential energy, the other one I'm going to call kinetic energy. Now, if I put into this same room $100, and I were to give 50 to potential and 50 to kinetic, I would still have $100 in the room. If I were to give 75 to potential, well, there'd only still be left over 25 for kinetic, because there is a closed system, so the money is still in the room. Even if I were to put in another guy by the name of friction, the money could transfer between each of these guys, but since the room is closed and no money can get in and no money can get out, it remains a closed system. Let's go ahead and apply this to the concept of work. So, we know that work is equal to force times displacement. So the force is actually going to be causing a displacement. On a roller coaster, a chain is responsible for pulling the cart up to the top of the hill. Let's take a look at how much work would be done. Let's do our regular problem solving. We know that we have a mass of 100 kilograms. We know that we have a height or a displacement of 40 meters. We also know that our cart is being pulled down by gravity, so the chain is working against that acceleration of gravity, and gravity is equal to 9.81 meters per second squared. So what is our target? We've been asked to calculate the work. We know that the work is equal to force multiplied by displacement. But if we look at it, we recognize we are not given force, so we'll need to calculate it. And we remember that force is equal to mass times acceleration, or in this case, gravity. So if we put these two equations together, we can recognize that work is equal to mass times the acceleration of gravity times the displacement, and that's the equation we'll use. So what will our calculation look like? Work will be equal to 100 kilograms times by 9.81 meters per second squared times by 40 meters. So, do the answer. You should find that work is equal to 39,240 joules. So now we've put in 39,240 joules of work, and we have given our object potential energy. Just how much potential energy does our object have? To find that out, we'll need to remember that our equation for potential energy is equal to mass times gravity times height. So the mass of our cart multiplied by the acceleration of gravity multiplied by how high above our starting point we are measuring it from. Let's go ahead and run our calculation. So what do we know? We know the mass is equal to 100 kilograms. We know that it has been lifted up a height of 40 meters. And we know that the acceleration of gravity is 9.81 meters per second squared. What is our target? We've been asked to calculate the potential energy. And, as we just mentioned, potential energy is mass times gravity times height. Well, we know all of those values, so our calculation will look like this. Potential energy is equal to 100 kilograms times by 9.81 meters per second squared, times by 40 meters. Running this, we'll find that our answer is 39,240 joules. Now wait a minute, isn't that the exact same value we had for our work? Yes, it is. The amount of work that we put into our system is going to be equal to the amount of potential energy that we give that system. So now somebody pushes our cart down the hill. As our cart begins moving, that potential energy is being turned into kinetic energy. And we find kinetic energy with using the equation kinetic energy is equal to 1/2 times mass times velocity squared. So, let's take a look at a couple of things. First of all, let's take a look at how much kinetic energy our cart has when it's about halfway down the hill. Now, to figure that out, we'll need to know the velocity, which I just happen to know is equal to 19.809 meters per second. So, what is it that we know? We know the mass of our cart is still equal to 100 kilograms. We know the velocity of our cart is equal to 19.809 meters per second. So, our target is our kinetic energy, which is equal to 1/2 mass times velocity squared. So let's go ahead and plug our values in. Kinetic energy is going to be equal to 1/2 times by 100 times by 19.809 meters per second squared. If we run our calculations, we will find out that our kinetic energy is equal to 19,620 joules. Now, it just so happens that if we were to also calculate what our potential energy is at that point, mass times gravity times height, we would find that our potential energy also equals 19,620 joules. Because here, at the halfway point, half of our energy is in potential and half is in kinetic. Now, what would we do to figure out the velocity at the very bottom of the hill? Well, first of all, we would need to know what the kinetic energy is. Well, if half of the kinetic energy is the exact half of the total energy at the halfway point, it's probably pretty safe to assume that our kinetic energy at the very bottom is going to be the same as our potential energy was at the very top. So our kinetic energy is 39,240 joules. We still know that our mass is equal to 100 kilograms. Now what we don't know, what our target is now, is our velocity. So how can we figure that out? Well, we're going to go back to our kinetic energy equation. If we know the kinetic energy and we know the mass, we can solve for the velocity. So we will multiply both sides by 2. So 2 multiplied by our kinetic energy is going to be equal to mass times velocity squared. Now we're close, but we're not quite there. So we'll divide both sides by mass, and then we'll square root both sides. So velocity is going to be equal to the square root of 2 multiplied by the kinetic energy divided by the mass. All we have done here is we've manipulated our equation to help us solve for our target value. So our target value, being velocity, we'll just plug what we know in. 2 multiplied by 39,240 joules divided by 100 kilograms is going to give us a velocity at the bottom of our hill of 28.014 meters per second. Now, I really want you to remember how to find this particular equation. So go back and review if you need to on how you go from our kinetic energy equation to figuring out velocity. Now, remember when I talked about the fact that energy is conserved. This means that our potential energy plus our kinetic energy is going to be equal to the total energy in our system. Just as we saw, the potential energy here at position A was the total of all of the energy that we had in our system at that time. So potential energy plus kinetic energy would give us our total energy. And this total energy does not change. Remember, when we were looking at our position B here, when our potential energy was 1/2 of what the original was, it was exactly matched by our kinetic energy, meaning that our total energy was still the same. And down here at the bottom, where our potential energy had gone to 0, that meant that all of our energy was in kinetic energy. And once again, our potential energy plus kinetic energy gave us our total energy. And that holds true for every point. If the system is closed, just like the $100 that I talked about earlier, the total energy is not going to change at any point in time in our system. Let's see how this works. We've got a roller coaster here, and this roller coaster has 3 points identified on it: A, B, and C. A is at 60 meters, B is at 30 meters, and C is at 40 meters. So, just knowing this information here, what the height of the highest hill is, and that we have a 100-kilogram cart, we can calculate the potential energy, the kinetic energy, velocity, and total energy for every point on this roller coaster. So to find our potential energy, we're going to use mass times gravity times height. To find our kinetic energy, we're going to use our total energy is equal to our potential energy plus our kinetic energy. And to find our velocity, we're going to be using the equation, the square root 2 multiplied by kinetic energy divided by mass. And remember, our total energy, once we figure it out, will not change. So let's start with our first section. For position A, at 60 meters, we would end up taking our mass, 100 kilograms, times by 9.81, the acceleration of gravity, times by our height, which is 60 meters. And we would find that we have a potential energy of 58,860 joules. Now, our kinetic energy at this point in time is 0. We haven't started moving, so our velocity is also going to be 0. Potential energy plus our kinetic energy is going to give us our total energy of 58,860 joules. Now, what is our total energy going to be for position B? 58,860 joules. What about for position C? You guessed it, 58,860 joules. What about for a position D, or E, or F, or G? As long as our system is closed, our total energy is going to be 58,860 joules. Is it always going to be in potential energy? No, because as our cart is going down, that potential energy is going down and the kinetic energy is going up. So here at the bottom of our first hill, we would, if this was all the way down to the 60-meter range, we could say that our potential energy was 0 at this point and our kinetic energy was 58,860 joules. Let's find out what it actually is here at our position B. Potential energy here would be our mass, 100 kilograms, times gravity, times 9.8, times our height of 30 meters, which would give us 29,430 joules. Well, if our total energy is 58 and our potential energy is 29, then 58 minus 29 will give us 29,430 joules of kinetic energy. Because our total energy doesn't change, our potential energy plus our kinetic energy will remain the same. Using our square root 2 KE divided by M equation, we figure out that our velocity at this point is 24.26 meters per second. Let's take a look at what everything would be at this point C. At point C, mass is still 100, gravity is still 9.8, but our height is 40. Running that calculation, we come to the answer 39,240 joules. Now, we know our total energy is 58,860. Our potential energy is 39,240. So we can figure out what our kinetic energy is. Subtracting 39,240 from 58,860, we get a kinetic energy of 19,620 joules. Then all we have to do is use our square root to kinetic energy divided by mass to figure out our velocity. This gives us, with a final velocity at point C, of 19.81 meters per second. You can see that using this simple process, you could figure out the potential energy, kinetic energy, velocity, and total energy for any point on this roller coaster system. Now this is idealized, meaning that it's not taking into consideration the gradual dissipation of energy due to friction and air resistance. But even when we look at all of those things, the system would still be closed. Things to remember. Energy is conserved, meaning it is not created, it is not destroyed, it is simply changed from one form to another when we are looking at a closed system. In a closed system, energy neither comes in from the outside nor escapes to the outside. Potential energy plus kinetic energy is going to be equal to our total mechanical energy when we are using our simplified idealized model. Otherwise, you could say potential energy plus kinetic energy plus Q, which is all other forms of work and energy, equals our total energy. Remember, potential energy is equal to mass times gravity times height. Kinetic energy is equal to 1/2 times mass times velocity squared. And that the work we put into the system is going to be equal to the potential energy we have in our system. I hope this helped.